Alors, bonjour à tous, j'espère que vous m'entendez bien. Alors aujourd'hui, je vais parler de Lakota, qui est donc une librairie qui s'inspire de Git pour stocker des thèmes séries. Et en fait, je me rends compte que je parle français et je devrais parler en anglais. So I will start with some basic concepts from Git, which are important to. I think they are not super complex, but they are powerful. So I think they are important to understand, even if you don't plan to use Lakota or anything later. So how does Git keeps track of your data? So the one of the big concepts behind Git are checksums. So checksum is a transformation that will transform a message into a number. You can see that, like, for example, you would have a Rubik's cube, and for each letter of your message, you spin your cube, and then at the end you will have a pattern, and this will be a unique pattern for a message. The important thing is that you can start again, do the same transformation, and you will have the same Rubik's cube at the end. It's the same idea here. So in Python, we can create checksums with hashlib. And so here I have an example of a message. So it's simply hello world, so it's a string. And if I compute a digest of that message, I have that long result. So it's behind the scenes, it's a number, but when we display it, we show it like that. It's a bit more user-friendly. And we can see that we can compute the digest of nearly the same message with one extra exclamation point at the end. And we get a completely different digest. So it's a way to resume a message with one number. Here I have really small messages, hello world, but it can be a long message, it can be a document, it can be a video. We can compute a digest out of that. So as I said, it's deterministic. So you compute the digest of the same message, you will get the same output. It's fast. Any small change will give us a different output, and it's impossible or nearly impossible to revert. Here the hello world is quite small, so you could brute force it. So try every combination of messages and hope to find your checksum. But it's difficult to revert, but we can store it. So again, in Python, we can create a small dictionary. So it's a structure where we can store stuff. And I can say, oh, my hello world, I will save it as, I will use the digest or the checksum as a key. And my other hello world with the exclamation point, I will store it with another key. And then I can access it back again. If I know the key, I will read my small dictionary called db, and I will get my message back. And just like we can compute a digest or a checksum of a message, we can compute a digest of another digest, or the digest of several other digests. You will see later why it's interesting. So those are the two digests of my two hello world messages. And so I can create a third digest that is the composition of the two previous ones. And again, I will store that in my database. So in my database, I will have a digest that points to two other ones. Again, I will do the same for a third message. So I compute the digest, I have this number. Again, I store it in a database. And similarly, I can once again create a digest of digest, or here a checksum of checksum. So I mix a bit the vocabulary, but digest, checksums, or even hashes are the same. So here I store a new digest that will point to my three messages. So those two are the hello world and the bye messages here. So if I push the ID forward, I can now I can now create a log. So a log is a simple list, and I will simply put not the digest of my messages, but the digest of digest. So this will, those 2 points to indirectly to my messages. So this means that if you know Git, you know with Git we can do a checkout, or it's similar to a pull. By giving you only one digest, or by starting with one digest, I can go in my DB structure, fetch the key, and then again get back my messages. So here the example shows the very last digest, and so it points to my three messages. I could pick the previous one and only see the two first hello. So not only in this case, so we started with a situation where one digest will resume the information of one messages, and here with one digest again, I can point indirectly to a collection of messages. Git behind the scene does the same. When you save some content into Git, you create a commit, and the commit is resumed by one digest. And Git will, just like we did here, Git will save for each file you want to save. For each file you want to save, Git will create a digest, and then will compute a digest of all those and return a final one. So with this one value, I can capture the state of a collection of files, which is a powerful abstraction. So based on that, I can easily detect file modification. So I talk about messages, but messages can be, for example, the content of a file. If any file change, of course, the digest of that file will change. And in Cascade, if we compute a digest of all my file, I will have a different result. So again, with one value, I capture the state of a collection of files, and I detect any change in any file. I can also deduplicate content. If I have several identical messages, I don't have to store all of them, because for each of them, I can compute the digest, detect that the result is the same, and know that I already have it in my database, for example. And the last interesting property is that I can ensure data consistency. So if my data was corrupted, I will obviously, if I compute the digest, I will get a different result than the one I expected. So I can detect that it's not the data has changed, there is something wrong, or a faulty disk, or a faulty transmission. If you want to read more about that, all those concepts are called Merkle tree. So it's this idea of starting with checksum of some content, and then compute the checksum of those checksum in Cascade, and create a tree of checksum. And the root of that tree captures the full state of the tree. So, as the title of the presentation was Git for time series, and so we have talked about Git concept. Now we'll talk about time series and what we can do with those concepts. So a time series basically is at least two series of values, a series of timestamp, and usually a series of float, so we can associate a value for each timestamp. And if we put those two series in a structure, a very familiar structure is data frame. If you don't know, a data frame is like an Excel file where you would have two columns, and in this case, a timestamp column, a value column. So the important thing is that values or content is organized by column. So here in Python, I can create a data frame just like that and save one value per day in the example. And so we computed digest for messages or files in the previous examples, I can compute a digest of those columns. So here I access my timestamp column, and I have a small transformation to do, but I can compute a digest. So I have my big number here. Similarly, I can compute a digest for my value column. And just like we did earlier, we can recurse. So I can compute a digest of digest. So here I've not put all the code, but you get the idea. So again, I have one large number that captures the state of my data frame. So here it's a simple data frame with 5 values. It could be 10,000 or 100,000. In the end, it's the same. I can have one digest for my data frame. If I do the same for a second data frame, so you see we had a data frame until the 5th of Jan, and now I have a data frame that starts on the 6th until the 10th, and I have similar value. And I could repeat that. So every 5 days, I create a new data frame. For each data frame, I can attach a checksum. And once I have covered my horizon, the part that I'm interested in, I can compute a digest of all of those. And so I have a full time series based on a list of data frames and one checksum for all that information. And so based on that, with 2 extra ingredients, and at least the 2 main ones, if we use compression, so if we have an efficient compression of the data in our data frame, and if we use remote storage, any key value storage would fit. So for Lakota, currently you are using S3, but we could use the equivalent on Azure Blob Storage. We could even use actually a SQL database with a simple table that acts as a key value. So any remote storage and compression, we mix that with this concept of digest. We have all the ingredients for a time series database, and we get all the properties that we showed earlier. So we have space efficiency because we have compression, but also the data deduplication. We also have ease of synchronization, because the state of my time series is one digest. I can communicate that over the network, or mostly over the network, and know if my data has changed or not. Also ease of caching. So caching, usually the difficult part of caching is invalidation. So how to know when not to cache anymore and refresh our local copy. Again, with digest, we have an easy way to know if the data has changed. We also have concurrent and atomic access. So the time series, the full time series can be, the state can be abstracted in one digest. I can have several states of my time series in parallel and save those in different digests. And just like we did a DB in the Python example, I can use also my file system, for example. So I will store on my file system a file whose name is my digest. And under it, in that file, I can store other digests that in turn will point to my actual data. And I can do that in parallel for different versions of the same time series. And based on that, I can rewind my data. So each time I change my time series, I will store it under a new name, which is my digest. I can get back in time through my log. So the same way with my log in my initial example, I can see different state of my collection of messages. Here I can see different state of my time series. So to show you that, I have a small example. So I've started with a database with two time series. Okay. It's quite slow. So I have two time series, Brussels and Paris. So currently it uses, if I remember correctly, 6 megabytes. Oh, no, I have much more. Sorry. Okay, I hope it will work anyway. Hope it's not too big. Oh, I know what I do wrong. So as I said, I have two time series, a total of 6 megabytes, and each one contains 500 megabytes. So I have over a million points in those time series. So here is the same, is a simple visualization. So I can show, for example, two different time series and show a value. So it's hourly values from 1970. So you see I have quite a big amount of data. And it's quite fast because I read, I think it's here 200,000 points without any issues out of the storage, simply because it comes from the fact that time series are compressed, so disk access is fast. And then I will quickly show you that I can pull data. So the same way I can pull data with Git, I can do the same here with my time series. So here it's a local repository, but it could be a remote one on S3 or a SQL database, for example. In this case, it's a 500 megabyte collection repository. It contains stock value from the NASDAQ, and the synchronization was faster when I was not streaming, but I hope it won't take too long. But basically, the bottleneck is the disk. We will max the disk performance because we are simply looping on all our digests. Those digests point to file, and we copy those files. So once we have that, I hope it won't be too long. Once we have that, I should be able to, the same way I was looking at temperature, I can browse those stocks. Okay. So as I explained, we can have concurrent access to a time series. And so the same way I can in Git commit locally some files, someone else can commit on his machine some files, and we can later merge those. Here, when I pull the data here, merge is not needed because I work on two different collections of series. But it's strangely slow. When I did the test beforehand, it was something like 20 seconds. Oh, here it is. Hope it's going to be better now. So now I should be able to search for, I don't know, some stocks. Yes, it works. And I can see. So here I have more complex time series. So for each timestamp, I have open, high, low, close prices, but also volumes. And here in this case, it's actually a quite small time series. I picked IBM because it's one of the oldest stock on the NASDAQ. So it started in 62. But it's a daily value, so I have, I don't know, something like a bit more than 10,000 values. So it's peanuts. But it shows that we can create a collection with a lot of time series in it. We have something like 7,000 stocks. So we have a lot of small time series. It's the opposite of my temperature where I have two time series that are very large. Yeah, the UI here is really a beginning. It's a work in progress, but it shows what we can do with that. If I see any question on the chat, I can answer. Oh, additional features. I have many ideas. One thing I want to do is to pre-compute some aggregates. So you have a collection, for example, of temperatures. I would like to be able to have a parallel collection that would pre-compute aggregates. So you could say I have hourly values in one collection. I will create an aggregate collection that will keep track of daily average, for example. We could have daily average value or daily max value for each temperature. Like that, when you ingest your time series in the repository, on the fly, we pre-compute aggregates and save those. I would also like to pre-compute some secondary keys. So in this case, I have one timestamp and some float. I could imagine, actually, I don't imagine I have that. For example, at NG, we store deals on the market. A deal is obviously a price and a quantity, but we can attach a lot of other information on those deals. And the same way, I would love to store aggregates, pre-computed aggregates. I would also love to store subset of those columns. So, for example, on a deals, I have a counterparty. Each time I save a collection of deals, the idea would be to list all the counterparties for that collection. Like that, if I want to filter by counterparty, I know where to look much faster. And yes, it works as a cache. So the same way I did a pull here to pull the data from one report to the other. I can also use, for example, if I access remote data, I can also say I will use a local directory as a cache. So the first time I read, I will fetch, of course, the remote data. The second time I read my data, the second time I read, the only thing I have to do is list remote file. I don't have to read those. If I list the remote files, I have the checksum, and I know my checksum are on my local cache. And so I have the cache was implemented since day one because it's super easy to implement, because we store content by digest, just like it. The same way when you pull again and again from a Git repo, you don't have to synchronize everything. You only pull the latest changes. And it's also it is also useful to detect changes. So you read some data, you do some computation, and then a few moments later you want to make sure your source data has not changed. It's really easy to detect that. If it has changed, you can recompute it. You have all those features for free. Okay, so if there are no other questions, I can wish you all a good evening. I hope that it was not too confusing. I think I started quite fast, but anyway.